Andrey is just a, I mean, oh boy. He did his PhD with Nachum Shimkin, who is another one of my absolute heroes. And Andrey's one of my newest heroes. We worked together when I was am I visible? We worked together when I was visiting NREL during 2018. And yes, I mean, I won't waste your time. He works on the topics, as you can see on this on this slide. Um,
Good. All right.
Okay.
Thank you.
Thank
So
you.
Andrey?
Yeah, thank you again thank you for inviting me to present in this excellent event. And I show here this first slide, and you can see the beautiful Colorado mountains. You can see also the wind farm or wind turbine in this case that Sean was so excited about. Unfortunately, I will not talk about wind turbines in this talk, but definitely it's an interesting topic that an application for this reinforcement learning methods that we heard today. So it would be interesting to see how this can be applied. Another thing that you can see here is also the date, which is wrong, but this stage, I mean, probably September 4th or 3rd, doesn't matter. Every day looks the same, so it's,
Some
no
part
really
of the
cares.
of course.
And sometimes, and yeah, exactly. Some people have September 4th already, so it's good. Okay.
yeah.
So what I will, so what I will talk about is on what I call here real-time system optimization. And you will realize very soon that this is just online optimization in the loop to a physical system. So this would be the main theme for this talk. And yeah, I hope you can hear me well, because sometimes I have internet problems. So I just wanted to check that the voice is fine. And
Perfect.
okay. So first, I would like to thank also the collaborators on this work. These are the main collaborators: Yue Chen, who is now at NREL, and he was former Sean's student, Aditya, Devraj, and Sean. And we have also other people that contributed to some of the things that I show here. I will mention them in the middle. But the main focus of this talk is about what could be called real-time system optimization. And to describe this setting, is quite simple setting, at least conceptually, is the idea is to look at a system, physical system, that is described by an input-output relation like this, where X represents the vector of controllable inputs, Y collects the system outputs, and HT is a algebraic system model. And here the model is assumed to be time varying, and I will tell you in a second also, again, the example. The running example in this talk will be power systems. This is the main topic of application of National Renewable Energy Lab, where I am. But you can imagine the application of these approaches to any physical systems. So I will write this as an input-output relationship like this, but you can also think of a more general case where this relationship is implicit, and the vector of outputs is determined by a system of algebraic equations rather than by an explicit map. And this is also the case in many systems, like power systems, for example. But for simplicity, I will just write a relation like this. So let me straight go to the example or the application that I will also show in the end. For people, and I'm sure people here, most of the people may not know what exactly power system is or how you describe it, but actually it can be described very simple by, well, at least for our purpose on this slide, by a network on the left side. So basically a power system looks like this. It's a graph that represents a connection of nodes via edges. Nodes are some nodes in the power network, and edges are transmission lines that transmit power. And the nodes here, especially the nodes that are highlighted, represent the nodes that can be controlled. So basically what we can control in the power system, in this particular example, we controlling power that is injected by different devices in the system into the network. So you can think of solar panels, batteries, electrical vehicles, and your appliances at homes that are injecting or consuming power. So basically X will represent in our examples the net power injection, which means, for example, if I have a house, then positive value would mean how much power is injected. If the value is negative, then it means that the power is consumed. So this is an example of what is the controllable device in that system or controllable variable. The Y, the output in such a system could be, for example, system voltages. This would be, again, the running example, but all different quantities in this system that are important for system operation, for stable and efficient operations, such as voltages, currents. You can imagine other things. Again, I will focus on voltages for simplicity. And this mapping HT is actually the famous power flow equations, which is a combination of Ohm and Kirchhoff laws, roughly speaking. So you can imagine that this is a set of algebraic equations that determines the system voltages given power injections. And this, again, in power systems, typically this is an implicit relation. But again, I will just, for simplicity, assume that this is an exact, explicit map. In other words, I will assume a single or unique solution of this system of equations given the input. And the third, the last aspect that I wanted to emphasize is the time varying aspect. So as I mentioned here, this map is dependent also on time. And this represents the fact that different elements in that system are time varying. So you can imagine that there are different loads here and different elements here that are uncontrollable, and they are just injecting or consuming power based on their own criteria or based on their own algorithms that you cannot really control. And these represent uncontrollable elements. And therefore, these are kind of the noise in the system. So that creates time variability in this map in a standard way. Another time variability comes from the fact that sometimes the system may be reconfigured in real time. In other words, the topology of this network or the graph that you see here will change, essentially meaning that you have a different constraint, input-output constraint. And therefore, again, this map can be time varied. And here, for illustration, I show also how the load and solar generation look like in those systems. So you can see here a profile of loads in 24 hours. This is showing, of course, this famous shape of the load, where I have the peak in this second half of the day. And the second plot here shows the solar power that can be generated by solar panels in this system. And again, it shows kind of more or less sunny day where there are no clouds, but you can imagine also different curves here that are much more noisy because of clouds in cloudy days. So this is kind of the example of power systems. Really, again, is in one slide, there is a lot of thing behind this, but in order to abstract the problem that we will be seeing today and give you an application example, I think this is enough. So we are talking about optimization. So really what we want to do in these systems, and the power system example is one example, is to optimize the performance of the system in real time. And I give here a very simple example of optimizing some cost associated with the output Y subject to constraints. And the constraints, again, for simplicity, I divided into two constraints. Again, we can add more things here, and I will add more things in a couple of slides. But to illustrate the concepts, I think it's enough just to consider the constraint, the explicit constraint on the input. And this could be, for example, engineering constraints on the devices that you have in the system. For example, a solar panel can only produce between 0 power and maximum power available from solar at any time t. And you can also notice that this is a time varying set because solar, of course, as you also saw from the profile here, is a time varying profile. Maximum power, this you can view it as a maximum available power. And moreover, again, during cloudy days, this is very volatile. So it's not very smooth. So it can change abruptly in seconds, basically. So this is the first constraint here. The second constraint is basically physics, right? You say, okay, you optimize your output subject to the connection between Y and X. So that's that is the simplest form of the problem that I will be considering. Again, I will also complicate it in a few slides to make it more practical. So again, the running example is power systems. So I just tell you what is the classical example of optimization in power systems. This is called optimal power flow. In that case, what you're trying to do, you're trying to optimize, this is again, very high level definition. I will define exactly mathematically what it means. But roughly speaking, what you're trying to do is to optimize generation cost and customer satisfaction in the system subject to device constraints and physics. And physics here will mean, again, these powerful equations that I mentioned before, Kirchhoff and Ohm laws. So yeah, this is just to give you an idea what optimal power flow is. I will give again the full definition at the end when I will show you the numerical example. So let me start with a couple of slides that talk about what can we do to actually optimize these kind of systems in real time. And let me start with a very simple idea, which I'm sure you all will agree with that simple idea, but I have to put it on the slide to make sure that what I present next makes sense. So the first idea is really to just solve problem one, right? So basically what happens, you have a time varying optimization problem. You just take your system model, HT, you compute maybe its Jacobian function, J or matrix, JHT, and you solve problem one, for example, using projected gradient descent. By solve, I mean, of course, in a generalized sense, you, of course, using the gradient descent, you will only arrive at maybe at a stationary point or a KKT point, depending on some conditions on the different functions that you have here. If the function f is convex and h is linear and set x is convex, then you are guaranteed to converge to an optimal solution by running this projected gradient method. And of course, you can run any other algorithms that you fancy, but that's just for illustration here. And I will go to, yep.
So the different time steps are not connected together by anything here.
So this, yep, that's an excellent question. So in this case, I'm considering kind of this online optimization setup, if you wish, where we have a sequence of optimization problems that are indeed just like repeated games, right? Where you don't have a connection between the time steps.
Are we going to consider regret or something like that? Like the best decision in hindsight?
Right.
Points are.
So yeah, there are two criteria, regret, as all probably people know here. And the second criteria that will be discussed, and I actually will show results on the second criteria, is just a tracking error. So how far the decision produced by an algorithm is from the optimal decision at that time. So these are the two criteria that I will.
In a nutshell, the difficult. So what's the difficult? This is a true online problem. What is being observed? What is known? What is not known?
Yeah.
I'm kind of confused about this.
So I will tell you in a second. Yeah. So let's for a second assume that you know everything. Okay. I'm just saying this is just the baseline, right? If you know everything here in problem one, you just solve it, right? That's the only thing that I'm
like you wouldn't even run projected gradient method, like you just like optimize for every single time step t, and that would give you, the best possible solution for every single time step t.
Yep.
If you're running gradients, projected gradient, whatnot, then you would lose compared to that.
Sure. Yep. So yeah, that will be on the next slide, and that I will talk about the online or running.
Is going to be clarified.
Yeah. So to clarify again, what I show on this slide is really a very stupid thing. Is just I say I have a problem one. If I have infinite computational capabilities, if I know everything, and if I can run projected gradient method to infinity, I can just solve the problem and arrive at a solution. So that's probably not very interesting. What is interesting here, I think, is just the structure that I want to show here. And this is what I will talk about in a second to get or connect to online optimization and to this model-free online optimization, basically eventually to gradient-free optimization that Sean presented in his talks. So basically the structure that I just wanted to emphasize here is the fact that since we are optimizing this system with this input-output relationship, it looks like this, right? We have a gradient descent where we have a Jacobian of the input-output map that multiplies the gradient of the objective function. And the objective function is evaluated at ht of x, which is the output of the system at the previous iterate, right? So this is just from chain root, right? It's not very surprising here. So my point here is that for systems, and we are talking about this real-time system optimization, where I was saying, and I mentioned before that we have high volatility of resources such as solar, high volatile loads. Basically, in order to solve this problem, we actually need to solve this problem every second in real time, and large scale systems, network systems, is becoming more and more problematic. So basically, just a solution of this problem in real time is not feasible typically. And second, this is to your question, Saba, is that what is typically happening in these systems is that you don't have a lot of those elements in real time. Especially, in this case, I will focus on the case where what you don't have is really the model. We assume that we assume that we know our objective function, which is a bit different from maybe machine learning, typical machine learning or online optimization approach, where what is unknown typically is just the cost function. Here, there is a bit of a structure where it's more, it resembles maybe reinforcement learning, right, because where in reinforcement learning, of course, we have multi-period problem, but here we have a single period problem or steady state problem. But what we don't know exactly is this map HT.
Yeah.
Okay, so
we also have a quick question from Renee.
Yep.
What's the typical difference for X and Y?
What is it, sorry?
The dimensions of X and Y.
Oh,
typically.
So that's an excellent question. So again, it depends on the system, but you can imagine in that kind of system, of a power system, X represents all the controllable devices that you have in the system. And depending on the system, if I give you a typical system, if you take Bay Area, San Francisco Bay Area, for example, you will have millions. But of course, typically what you would do, you would subdivide the system into subsystems, and you would do some hierarchical control and optimization where you optimize areas in the system. And you might have hundreds to thousands of inputs, which represent controllable devices in the power system. And then the output could be similar. It depends on how much. Remember, the output here that I described in the power system was voltages. Voltages could be, depending which voltages you want to, that you care about. At most, you will care about the voltages of all the nodes in the system. So the size of Y will be the size of the number of nodes in the graph of the network system that you have. And similarly for X, right? At most, it will be the size of the number of nodes, basically. But yeah, it could be, of course, less depending on what you can control and depending on what you can measure and what do you care about in terms of outputs eventually. So I hope this answers this. So basically, so yeah, I'm just coming to this subtle point that says, okay, here, if we want to do it, it's not only that we need to solve this problem in real time, but we also need to know the model. And again, this is kind of the common theme in this reinforcement learning, I guess, bootcamp, is that we are trying to do something from data, right? Or in that particular case, what I talk about here is that I am moving from this open loop or feed-forward optimization approach to feedback optimization. What do I mean by feedback here is, it's a bit vague when I say it in the title, but the idea is shown here in this diagram. Basically what I do, I put the optimization algorithm in feedback to the system. And here you go, you also see the online suddenly, right? So instead of solving the algorithm, solving the problem, since anyway, I cannot solve it, and maybe I don't have to solve it, especially if it changes fast. So what I could do is really to do our famous online gradient descent, right? So equation 2 is just online gradient descent. The only subtle difference here is that since I have this system in a loop, I have this term here. This is what I want to emphasize. So when we talk about this system, real-time system optimization, what we talk about is this feedback interconnection where the online iteration of the optimization algorithm acts on the measurement of the output at time k. And now k is identified with the time and not iteration, actually. So basically you are, in this particular example, I'm doing one iteration at every time. Of course, we can think of doing more than one, but this is kind of the extreme case where I do one iteration. And again, here you can, again, I'm still assuming that I know f. So maybe again, a bit different from online learning, online optimization in machine learning, where maybe you assume that you don't know f at time k. I assume that I know it, but what I don't know really is this relation between y and x. Instead, I just use the measurement. And this looks very simple, but conceptually it creates feedback interconnection. And there is, of course, then all the questions associated with stability and of basically control theory questions that arise when you do that. So still one thing that I want you to notice here is that although now suddenly, by the way, notice that it becomes model free, almost, right? Because if you compare to, if you want to do online optimization with using this iteration, you need to know H, right? But if you close the loop and you are able to measure Y, you don't need to know H, you just need to observe the output and go to the next iteration. And if, by the way, the problem, oh, sorry, yeah.
Yeah, don't you need to know JFK, the check?
Okay,
check of
yeah, so excellent. So that's my point here, right? So although by doing that, we closed the loop and we made it almost all model free. So still it's model based because you need to know J. Yep. And J represents in some sense sensitivity of input, of output with respect to input, right? So this is something that in practice, for example, in power systems is a bit less problematic to obtain, but still it requires knowledge of the model. The good news is that because it's feedback here, and because any inaccuracy in Y will be corrected by this feedback loop, even if you have inaccurate J, this algorithm typically works, provided that J is almost in the right direction. But again, you cannot know it in advance. And obviously it is becoming even more problematic when J changes abruptly. And J can change abruptly, for example, if in this power system, for example, we change a configuration and we change, I don't know, here I didn't show switches, but imagine that you have switches in this graph that make the topology of the system completely different. In that case, J might change abruptly and sensitivity of one node with respect to other node might be different from one time to another time. So this is, yeah, so this is the main disadvantage in this approach, is where you still need to know J. And this, if you agree with this slide, I guess this motivates the next slide, which again, probably will be not too far away from what you already heard from Sean. And the idea is to replace the gradient. So instead of going to this gradient first order algorithm, we can go to and apply zero order approximation of this function. So here I'm talking about this composed function of f of output of as a function of x. And again, you have this gradient here that represent we have the chain rule with the Jacobian. So instead of computing this gradient like this, what we propose is to use zero order approximation. And Sean already showed all these different variants. So let me just come back in this slide just to list some of the options. So the first option that Sean showed, what was I think 1A in his slides, was single function evaluation. Again, this is very, people that know bandits optimization or extremum seeking will know this, right? This is how things are typically done in this literature. And this requires single evaluation of the function at a perturbed input. And the perturbation here is using some exploration vector C and a control parameter, controlled parameter, small scalar epsilon. The second variant that also Sean showed was the two function evaluation, which basically looks like numerical derivative in generalized to the vector case. And there are also other options where you increase the number of evaluations and you do an average of those. And I didn't show it here, but you can imagine how you can increase the number of evaluations to improve the accuracy of these kind of approximations. So in this talk, I will focus on this two-function evaluation approximation. Again, you can think of others. The main motivation was also explained by Sean, I think. So one motivation is, first of all, that if you do the Taylor series expansion, and if everything is really ideal here in the sense that you do this exploration at the same time step, right? So it's a bit of an approximation. Of course, once you do one input, you apply one input, x plus, and you apply other input, x minus, the system already may be changed. But assuming that the change is not big enough, then you can implement it. Otherwise, you need also to account to the variability in the function in between the two evaluations. But let's assume for a second that it's not happening. So one good property is that this approximation is actually looks like this, right? Is this low rank matrix times the gradient plus an error term that is of order of epsilon squared. And actually, if we have a quadratic objective function, this term is actually zero. So basically, it's even better, right? So this is one motivation for using these two evaluation. The second one is that it has nicer properties than single evaluation. Sean touched upon those, I think, in his talk. First of all, it has smaller variance. It has Lipschitz properties, right? Because if you look at this, especially for the case where this epsilon, this term is zero, you obviously see that this approximation has the same Lipschitz properties as the gradient, which is typically a standard assumption in any analysis. Yeah, there are other advantages. And of course, we can take more evaluations and do averaging, but of course this requires more evaluation, so this is becoming more computationally complex to implement. So I will focus here on this kind of practical case where you assume we can do these two evaluations. It is enough to have nice properties and fast convergence. But of course, people can think of just standard bandit optimization where they use this variant as well. And this works in practice with a bit slower convergence, I would say. And what I will show for power systems will be based on this approximation. So with this approximation, I guess I convinced you that we don't need anymore anything in this interconnection loop, right? We don't need anymore this Jacobian. We don't need anymore the mapping HX. We just need to be able to approximate this term with something like that.
By the way, can I have a quick question, clarification question?
Sure.
This admits this approximation where you have this big epsilon squared term. It seems to suggest that you should just make epsilon go to zero. That's not true, right?
Right.
Something is missing here.
Yes. So I mean, you can see that if you take epsilon go to zero, obviously this becomes, right, if you just look at the equation, there is this term that goes to zero and this term that goes to zero, right? So in principle, you could take epsilon go to zero, but as far as the convergence goes here to of this denominator, I think you will have a problem in
I think something
right?
going on with the variance, right? Like this
right.
more like speaks to that unexpected.
Right. So there is a trade-off between So there is a trade-off between the variance, and I didn't show it here, but it will appear in rates actually. Yeah. So obviously, yeah, if you take the epsilon to zero, you will have, as usual, you have this trade-off there between the the transient term and the term where you convert, like the asymptotic neighborhood of the optimal solution, and you will have a trade-off. But yeah, I didn't mention it here. But obviously, yes, if you have epsilon equals zero, it will not work. Yeah. So okay, so yeah, and I'm happy to take questions in between. That's just let me know. if there are questions appearing that I don't see them. So what I wanted to, yeah. Oh.
I let you know.
Thanks. Yeah, okay. So what I have on this slide is, I will not go through this. You can imagine that there is tons of literature on gradient-free optimization in general, including from the history that Sean was talking about from 100 years ago, more or less. And extremum seeking is one method that looks like what I show here. And you have, of course, SPAL, and even in the beginning of 90s, which is similar idea, SPSA. And recently there's a lot of work on gradient-free optimization and bandit optimization, where, again, very similar concepts are used, but the bandit optimization there and this type of literature that I show here is more on machine learning applications where there's no really system in the loop. And extremum seeking is actually very close in spirit to what I showed here. So, because it talks about adaptive control, and what we are doing here is in some sense a way of adaptive control. So, so the focus of this is about, first of all, I want to make, the focus of this presentation is about constraint problems. So I'm talking about constraint time variant problems, and I will go into more detailed definition in a second. And the idea, as you saw in power system example, is to show power systems, or in general network systems, and how we control them in real time. The second point here is deterministic exploration. So this is coming back to Sean's talk about quasi-stochastic approximation. Sean, I think, motivated quite a lot of why using deterministic exploration signal, the signal C that you showed, rather than a stochastic one. And the third point here is about practicality, right? What we're trying to do here really is something that can be applied to these large-scale systems, such as this power system. Therefore, we are looking for online distributable light, let's say, methods. And you will see we will be talking about primal-dual methods. And you will see an application to power system in more detail. So let me go quite fast. On this slide, it's not too interesting. It's just an extension of this basic problem that I showed before, but to a system, a network system. So we have n subsystems that are interconnected via a network. Again, this is the actual example of power systems. This is how power systems optimization problem looks like, problem 3, where you have n agents that can optimize their own power injections, such as solar panels, batteries, or aggregations such as houses, right? And they have their own constraints, operational constraints. And then there is a set of constraints imposed on the system output, right? So this is just an extension of the previous problem, where I also add constraints on the system output, as well as costs in terms of system input. And knowing optimization, we can define a Lagrangian of this problem, right? Let me just go to the next slide. And what we are trying to do here is, or maybe, yeah. What we're trying to do here is really to define what is the optimal solution. So under technical assumptions, if you formulate the saddle point problem for this problem 4, then X star and lambda star, the optimal solutions of this saddle point problem, coincide with the problem solution of problem 4. At least X star coincides, and lambda star is the optimal Lagrange multiplier. So what we are doing here is regularizing, and there is a motivation behind this. So I'm not just taking a Lagrangian here, I'm taking a regularized Lagrangian. So regular Lagrangian is this term. I don't define it because I hope you all know what it is. But what I add here is 2 regularization terms. These are standard L2 or Tikhonov type regularization terms that make this Lagrangian strongly convex and strongly concave. Strongly convex in X, strongly concave in lambda, assuming that everything else is convex, and so on and so forth. So, and the reason behind this regularization is kind of practical, to make convergence much faster than in cases where you don't have these strongly convex or and concave properties. So from now on, you will forget about problem 4, but you will just remember that Z star is the optimal solution of this saddle point problem. So this is our desired trajectory of the system, and the online algorithms are trying to track this desired trajectory. And as Shabai was mentioning, the criteria will be a regret, which I will not show today, but in this particular case, it will be just a tracking error between Z star and Z that is produced by an online algorithm. So the online algorithm that I will be talking about is this primal-dual algorithm, where at each time, this is kind of standard primal-dual algorithm with some simple twist, again, feedback that I will show in a second. But yeah, I just divided it into steps to make sure that we are connecting to the real system. So it's not just an optimization algorithm. Remember, it's an algorithm that is in the loop to the real system. So what we are doing at every time step k, we are applying input xk. We collect measurements of the output y hat k. We compute the gradient of the Lagrangian with respect to x. We perform the primal step. We perform the dual step, and we repeat. Okay, again, I will not go into the details of this because this is kind of a standard primal-dual algorithm, online primal-dual algorithm. But what I want to emphasize here is, again, is that this feedback thing, right? So in a standard optimization, that will be it. But here, what I'm trying to say is that actually we are closing the loop, and what we put here in these terms is the system output or measured system output, what y hat. And again, this is the model-based version, right? Because you see, I'm still using the Jacobian. So it's model-based in the sense that it requires to know what is the sensitivity of output with respect to input. Now, as I showed in the previous slides, for the simple problem, we can, in the same way, extend the zero order algorithm to this setting where we need to explore, right? We explore at x plus epsilon c and x minus epsilon c. Again, here I assume that we are able to explore at the same time step without moving to the next time step. Otherwise, we can do also the other one, which makes the analysis more complicated, of course. And we collect these measurements. Again, here I also assume that I apply to the system a third input, xk, which is in the middle. This can be also avoided. We don't need to do it. But again, for the analysis, it's much easier to assume that we also have xk as the actual input to the system. So we just perturb plus, perturb minus, and then we go back to the actual x. Again, it means that we have three evaluations. But if we have 2, we can also do 3 in some sense. And once we have all this, we can just replace the gradient part that associated with the output with the zero order terms. I don't go into the details, but you can imagine this is just an extension of this zero order Kiefer-Wolowitz or other names that you can think of to this problem where in the Lagrangian we replace the gradient that associated with the output with these terms. And again, primal step is the same and dual step are the same. The only difference is that the primal step is now with approximate gradient. Again, see, look, just notice it's still a feedback interconnection, right? Because what we're using here is really the measured output of the system rather than the, an output that you could compute from a prototypical model of the system that you might not have in real time. So I will go quickly about the analysis. This, again, so you can imagine, since I'm talking about this you can think of this as quasi-stochastic gradient descent, like what Sean presented. It could be put up to some extent in the QSA theory, but it can also be analyzed, at least the convergence could be analyzed directly. Especially in this case, I'm showing you the conditions for direct analysis where we are using constant step size. Notice that opposed to what Sean showed, where he had these vanishing step sizes, In this particular case, we are using a constant step size, and there are several motivations behind that. One motivation is because we're talking about time varying problem. It makes more sense to use a constant step size, although again, depending on which metric you are using, for example, for regret, you could use also a vanishing step size, maybe something like 1/√t. But for that work, I assume here that the step size is constant, small constant number, and I will choose a constant step size to have some guarantees on stability and convergence. So some assumptions, I will go quickly over that. First assumption is on the exploration signal. This seems a bit restrictive. Again, this can be relaxed. For simplicity, I'm showing this one. It talks about the sample covariance of the exploration signal. Remember, I'm talking about these deterministic signals, such as the sinusoidal signals that Sean mentioned. And under some assumptions, you can make this be identity. Actually, we don't need identity, we need positive definite matrix. Again, for simplicity, assume it's an identity. It could be achieved by using some sinusoidal signals and taking t be some common integer multiple of the periods. It's a bit of a restrictive assumption, but again, we can relax it to some assumptions where you have a positive definite matrix and that still will work. The second assumption for analysis only is that we have some issues with projections. I have to say in these algorithms, right? Remember that we have all these projections here. The version that we have now, and actually we have now other versions, but for this talk, what I have is a version where we assume that the projection is not active at every time step, but also only these big D time units. Again, this can be relaxed, but let me just put it for analysis. The third is assumption on variability. This is just telling us how far or how fast or how much the optimal trajectory varies. So Z star, I remind you, this is the optimal primal dual pair. And we have a bound on the variability of that. We have a bound on the variability of gradients, and similarly for other functions. Again, notice these assumptions are a bit more restrictive than the standard regret analysis, but this is because I will be talking about tracking result rather than regret result. For regret result, actually much more relaxed assumptions can be imposed to get a regret result. But let me just show you that one. And finally, since I was talking about measurements, remember we have a measurement of output, then we need also to assume that something about the measurement error. And for that particular case, we assume that this is just a bounded measurement error. You can also assume stochastic, standard stochastic assumptions on the error. But for that one, we assume just bound EY on the measurement error. And then there is this stability or tracking result that tells us that if you can choose a small enough step size alpha, and that basically, yeah, the only thing that you can basically tune here is the step size alpha and also this parameter epsilon, but mainly parameter alpha that will result in a bound, asymptotic bound, like shown here, where alpha is a step size. Again, this var epsilon is of order of different parameters that I just defined, of alpha, of epsilon squared, EF, EY. Sigma, I remind you, this is the time variability of the optimal trajectory. And C will be less than 1 if you choose alpha accordingly. And again, this result doesn't show this trade-off with epsilon and with alpha. Obviously, yeah, you can take alpha equals 0, and that seems like it will work, and epsilon equals 0. It will not work because of the transient term that I just omitted here for simplicity. But yeah, this rate here of how fast this converges to this will be affected by the different parameters here. But the overall idea is that in asymptotically will converge to a neighborhood of this trajectory, and the upper bound, really the worst case bound, will be something like that. This is based on analysis of the primal-dual method that I showed before, which becomes actually an approximate primal-dual method with this zero-order approximation. So this is kind of a standard analysis. And this result can be interpreted, for example, as just a stability result that says that trajectory input to state stability, these kind of types of results. So I have some time left, and in the remaining, I will not go into the proof. I mean, there is a paper in ECC that we prove this result, and we also are looking into how to also fit it into the QSA. You can imagine that it's doable, but it requires a bit of more work in terms of the assumptions that Sean presented in his work. And in the remaining time, I just really want to give you an example of the application, because I guess this was kind of the main motivation for my presentation here, is to show what we can do with these things. And this is, I think, is kind of exciting. And one example that Sean was talking about, the wind example of wind farms, is interesting. The example that I show here is what we're already doing now, is how you can optimize in real time different devices in this power system that I showed you. And you can see here is a bit more complicated example with 123 nodes. So you can see here 123 nodes. In this particular simulation, we only had 11 controllable devices, but this is easily extendable to much more devices that you can control. The rest of the devices were just uncontrolled. And you can see the uncontrollable elements again. This is the driving signals for those elements, such as how load looks like or how the solar looks like. And another thing that happening here in this example is that the network actually can be reconfigured, as I mentioned before. So in the middle of the operation, you suddenly can have a new topology, a new graph that represents this system. In other words, this function h there that I showed changes also because of that. So optimal power flow, remind you what it is. It's really optimizing the cost of different elements here, such as generation cost, customer satisfaction, subject to physics constraint and device constraints. And this is explicit definition of those device constraints, in particular case of this power systems optimization. Again, I don't think it's maybe not very interesting going into details of physics here. So I don't want to explain to everyone what is active and reactive power because it requires another 1 hour. But you can imagine that these devices, the solar panels that you have, they can basically, you have 2 knobs there. One knob is the active power, which is just a regular power that you can imagine that the solar panel can produce. And there is another knob, which is a reactive power, which helps to do other things. It doesn't do much for energy, but it can, for example, help with voltages in the system. So you can turn this knob and you can turn these knobs, and there is an interrelation between these knobs via some constraints that are shown here without going too much into these details. But I do want to tell you what are the objectives. So the objectives really are two main objectives. One objective is to what could be called emulate a virtual power plant out of this feeder. So in other words, think of this, the term feeder, maybe people don't know what it is. Okay, think of a neighborhood in a power system where your house is connected, and this is the system of the neighborhood. And think that you want to make a virtual power plant, basically of this neighborhood, by controlling and optimizing the different devices in real time. In other words, what we are trying to do is to dispatch this feeder or this system and make it follow a given power signal at the connection point of this system to a larger grid. So instead of using a regular power plant, you're kind of creating a power plant out of a collection of devices that sits in people's houses. So this is kind of the idea of virtual power plant. It's very popular now with all this massive penetration of resources such as solar and batteries and so on and so forth. So this is one goal, is really to follow the feeder head power. This is what is called, what is said here. You are just trying to track a given power set point for the power that flows at the connection of the system to the main grid. And the second main objective is regulating voltages. So while you do that, you have a constraint on voltages. So you want to keep the voltages within pre-specified bounds. And you can think of these two as constraints on the output of the system. So once you control the system, you tell the solar panel to inject certain amount of power, or you tell your battery to inject a certain amount of power, this will result in certain voltage in the system and in a certain power that will flow in the connection of the system to the grid. And this actually is the system model, right? That we don't know in the power system because of different elements that I described before. So we can see here some of this behavior that I told you before. If you don't do anything to the system, this is what you will see. This will be the power that will flow at the connection of this network to the grid. And here I show example of two networks. Remember, we have two configurations of the network. I didn't show it here, but I actually, by two configurations, I mean that I have two possible configuration of switches in this network. And we have these two modes here, one network 1 and one network 2. And you can see that on the voltage side, so this shows the voltages, you can see that the voltages becoming very different when the network switches to a different configuration. And from the operating perspective, from the optimization perspective, we don't know those things. We don't know when this switch happens. We also don't know what is the configuration of this network. The only thing that we can do, we can only measure these outputs, these two outputs in that case, and do something with these outputs, as I showed in this feedback interconnection. So for example, the output here is one number for power, and there is a lot of numbers for voltages, because voltages here represent all the voltages in the system. And this is what happens if you apply this algorithm, the primal-dual online algorithm. Basically, you are able to track a given signal. So this step signal is the signal that we provide. So this shows kind of the virtual power plant. We are able to make this system to follow a given power signal. And we're also able to regulate the voltages within bounds. So in this case, we wanted to impose lower bound constraint on voltages, which is 0.95. You just think of this voltage as a normalized value between 0 and 1, and you need to keep it between above 0.95. So this algorithm, without knowing that we had this reconfiguration, without knowing what are the actual system elements, or what is a system model, was able to regulate the voltages within bounds in real time. And finally, what I want to say, yeah, I know that I'm a bit running out of time, but what I wanted to say is there is some question about noise here, right? Remember that we have measurements, and all these algorithms, of course, will be sensitive to noise. So depending on how much noise you add to your measurement, you will see deterioration in behavior. What we observed is actually there is certain threshold behavior that could be explored also analytically. We just observed it numerically so far, that up to some level of noise in voltage measurements and power measurements, you have very good behavior of this interconnection. But after some threshold, there is a fast deterioration in performance. And luckily, this bound here, or this threshold here, is above the standard measurement noise typical measurement devices. But yeah, it's still interesting to see why we have this interesting behavior like that. So yeah, I will stop here. I just want to say, yeah, this is the summary. I know that we wanted to have some time for questions, but yeah, I will stop here, and I'll be happy to take any questions.
Thanks. So there is one question that came from Gerge. He's wondering about whether the tracking error is going to imply something about constraint violation error, constraint violations.
Yeah, that's a very good question. Yeah, thanks. Actually, so the tracking error that I show here is both on primal and dual variable. So it implicitly implies things about constraint violations. However, there is also a way to analyze the constraint. At least we analyzed in some instances also directly the constraint violation and showed bounds on constraint violation as well. But in this particular result, since Z includes both lambda and X, it just tells us how far we are from the optimal primal dual pair, and assuming that when we close to optimal primal dual pair, we also close in terms of constraint violations. But yeah, I mean, the analysis of constraint violations should be done in addition, I would say, if we want to have an explicit bound.
Yeah. An unrelated question that I have. How far are we from deploying algorithms like this in the wild?
Well, yeah. Yeah.
Yeah.
Yeah, no, please go ahead. You wanted to complete your thought. No?
No, it is just like, is this already deployed, or is it going to be deployed, or what are the things that need to be addressed before you could deploy something like this?
So the quick question is, it is quite close to be deployed in a sense that what you see on this slide is going currently into some commercialization. Again, this here, and the difference between this slide is that we use Jacobian and we don't use Jacobian in another one. But yeah, so in terms of applicability and where we are here in the demonstration of this, we are kind of quite far now. The problem, so let me say where we are now. So we demonstrated it on real microgrids in California. And we demonstrated it on a real distribution feeder here in Colorado, not in the mountains. Actually, the co-op, the electric co-op that operates one of the ski resorts. And it is moving forward. The only problem is that utilities, which are kind of the natural customer of this kind of algorithms, are not very forward-looking generally, let's say. So it's very tough to push something like that to them unless they really see why you need it or what is going on if you don't do it. And they gradually seeing the need for that, especially when you have more and more these very fast-acting volatile devices on the system edge that you need to control and coordinate in real time. But it takes time. So to go further in this process, you need some time and understanding from utilities, or you need companies, other companies like, I don't know, Tesla, Google, that will take over and will do those things instead of utilities. So, and it's going there as well to some extent. So I guess in parallel, we are working both with utilities, which is, again, it's pain usually, and also with some companies that are a bit more forward-looking, and they are trying to use backdoors to deploy those things without really directly interacting with utilities. We have some recent, yes, recently we had a company that was interested in actually deploying these algorithms, because I mentioned that these algorithms can be distributed, right? So you basically want to run the instances of this iteration, for example, when you distribute it between different agents in people's houses, for example, right? And one thing that we're doing now is we are partnering with smart meters company, because smart meters are very extensively installed in people's houses. You have this smart meter, it doesn't do anything there, but it has a computer that sits in your house and can basically perform these algorithms. So we are trying to partner with them to push this through smart meters and kind of telling utilities, oh, by the way, you already have this, right? You don't need to do anything. You just need to run software and see how it works. So it's kind of a backdoor approach to utilities. So.
Okay, so just talking a little bit around this applicability. So the time scales that you're looking at, like what are the optimization steps or optimization steps, time scale relationships?
So here the motivation behind this loop here was really fast scale. So what we are talking about is really seconds. So we assume that we do this iteration. So yeah, if you really want real numbers and like real units, then we do it every second or 100 millisecond, let's say, whatever time scale. But this is kind of the ballpark. We apply it to the system, we see the output, and basically this loop has to be closed in this kind of seconds time scale, which means that we need very fast measurement capabilities as well in that case.
And compute as well.
And compute, yep.
So that kind of leads to the distributed applications or distributed implementations, I guess, because maybe on this time scale, it is a bit challenging to implement a centralized algorithm. So what are the challenges if you want to distribute this algorithm? It is written as a centralized algorithm here, but
right. Yep. Yeah, that's again, yeah, it's exactly the line of thought that we have now in terms of how we scale it, and scalability is dependent a lot on this distributability. And the one version that we have now that is kind of the more commercial, what we're trying to commercialize is this gather and broadcast. I don't have the figure here, but you can imagine the idea, right? So this iteration here, if you think of this as a Cartesian product of individual constraints of all the devices, you can just distribute it, right? So you can just write it for each element, and you have and then what you need is to communicate to these guys here, xi, let's call them, right? I think I have it here, right? So basically, right, this xi can be computed locally, projected locally. The only thing that you need really to communicate is Lagrange multipliers associated with the network constraints, because whatever everyone does affects everyone else, right? So, so in terms of the output. So one standard approach is really this gather and broadcast. So what it means is that you have a central entity that is able to measure the outputs of the system or gather this measurement, which is fine. This could be like, for example, a control center of a utility. They do it now already, and they get fast measurements of voltages. They compute this iteration. This iteration is very light, right? It's just nothing here. And they send this lambda down to basically broadcast the vector of Lagrange multipliers to all the devices. And then every device does its own optimization based on the element of the Lagrangian with taking into account the Lagrange multiplier. And this is kind of the standard. We call it distributed. It's not really distributed because it requires a centralized entity. This is one approach, let's say the simplest one, conceptually at least. And also, of course, we are looking into more consensus-based approaches where you don't have this central entity, but you have these measurement entities that can measure things and they can communicate between each other. So they can communicate Lagrange multipliers between neighbors and basically propagate this information. So more like a consensus-based implementation of these algorithms. And it a lot depends also on the actual architecture that you have in these utilities and the power system. So yeah, if you have a central entity like utility and it can gather measurements and it can broadcast this Lagrange multiplier, then you can do it. But if you think about completely distributed case where there's no like master slave, yeah, there's no master slave, right? It's just everyone is just doing something, then it's more like consensus-based approaches that would fit here.
Okay. All right, we do have some questions on a Q&A. Have you tried various forms of this injected inputs, the what was sinusoidal in the case of
sinusoid, yeah. So in this case, we tried sinusoids. We also tried, before going into this, we also tried the stochastic perturbations. And we saw these effects that, that Sean showed on his slides, where you have much more noise and much slower convergence. So we went, so that was the main motivation to go to this deterministic perturbations, especially since we're talking about online real-time implementation, where you need to do these things fast enough to cope with changes in the system. So if of course, if you let the system to converge and the convergence will happen in 1 hour, and maybe the system already changed. So we want to have really fast convergence. And it showed that this basically we could see that this deterministic signals led to faster convergence. And also when using this thing, this Kiefer-Wolfowitz, let's say, idea, it was also faster than using and less noisy than using the single evaluation, that kind of standard bandit idea, or zero order
I guess
approximation.
here the question is like, how much did you explore like frequencies for these sinusoids? How much does it impact the result? How did you tune this?
Yeah, so yeah, we explored different, yeah, so the frequency should be fast enough to, yeah, we explored those. I think what we showed here is more like one of the optimal results based on this exploration. So of course, I didn't get too much into this, but you can see that these convergence rates here. So for example, this shows how fast you are able to bring the voltage back into the bounds. Right, so here, of course, it shows it's very fast, but if you zoom, you see that it takes some time. So based on this exploration of frequencies of the signals and the magnitudes of epsilon and everything, yeah, it was more like a trial and error, I guess, for the simulation to see what works best. But yeah, I don't have exact details because the simulation was done by UHN and it's not here, but I know that we did a lot of exploration for how to choose these parameters, how to choose these signals, and we can give you more details if you ask
I guess
me.
the time just need to be matched in general. That would be the idea. So there was also the question, it's somehow related to this time scale question, that you're assuming simultaneous measurements, multiple simultaneous measurements of the outputs, which is not feasible in this application or other applications. So how do you deal with that? Like, do you have any thoughts about whether we should resort to the single measurement or just push through the two measurements, not caring about that the system might have changed a little bit?
Yeah, that's a good question. So indeed, these assumptions kind of say that within the time step, the system didn't change, right? So, and I mean, it just means that the time scale of my control, which was 1 second, should be faster than the variability of the system, the map HT. So if we want to go into faster, then so basically, if we just, I mean, we can just assume that we do one evaluation every time step, which is fine. I think it also works. In practice, it worked because what we did really is we did this not within the same step, but we really evaluated it one by one, and system changed in between. So in terms of performance, I think it didn't matter much, again, because there was not much variability within 1 second when we did it. But if you want to account to this variability, it could be done. And I think we, yeah, in the upcoming paper, we will be doing that by incorporating these bounds on how much system changed within 1 step, incorporating them in the bound, in the convergence bound, in the tracking bound. You can do it. Then you will have another term with the tracking. In the tracking bound, you will have another term here that represents this variability as well. Here, this bound assumes that there is no variability within 1 step. If you assume there is, then you will have something here that will account for it. So this is kind of the easy answer to this. But of course, the faster your system changes, the less good this thing will be, right? So basically, I would say the easy answer will be you need to perform control and this probing of the system faster than it changes. So.
Mm-hmm. Good. So Renee is asking, did you compare the performance of the fully centralized case to the fully distributed case? I guess you haven't, because you haven't implemented the fully distributed case, or did you? Like the price of anarchy in game theory, right? Like what's the cost of fully decentralizing? Have you implemented any of these consensus-based algorithms or any of these ideas? Have you experimented with that?
So by fully decentralized, you mean what? So yeah, I just want to
clarify. It is, yeah, like maybe you can observe your neighbors and your neighbors can send you signals and whatnot, this sort of thing.
Yeah.
You know,
so
the network-based.
So maybe peer-to-peer communication rather than centralized.
Well, and respecting the topology, I guess, because you don't expect to be able to, you know, phone up like arbitrary units.
Yep. Yeah, we have actually developed algorithms for this peer-to-peer communication with the communication graph that is not necessarily the topology of the system, but it could coincide or could not. I mean, it depends. Sometimes it doesn't have to be. So you have a communication graph and you have a system, like physical system graph, right? So we have algorithms that, yeah, I can send
yeah, if you're on
yeah.
Discord, you could just point us to some papers on that.
Yep. Or I can put I can put references inside these slides, for
I
example.
assume maybe like references to where slides.
Yeah, I mean, I can either put it on the slides or wherever you would like me to. I can add more references and yeah, whatever is best for. I'm not sure where it's better to put it. So.
Well, there is this discussion thing app that it would be idea to put it there.
Discussion, you mean in?
I Discord server is like a Slack clone. I give you access to it.
Okay. If you yeah, just let me know where I can.
And then
yeah, okay.
Yeah, and okay. So next question: what are interesting applications other than power control that this online feedback primal-dual algorithm would be good fit to? Is there a main structure in the power control problem that was exploited?
Yeah.
How specific is this to power control?
Well, you know, on the high level, not much was exploited here, right? As you can see, I was just saying we have an input-output system, and in the fully model-free case, it was basically in the fully model-free case, we didn't assume any structure for the function h. In the previous version here, we assumed that at least this Jacobian here that you can compute, which is kind of minor. Well, minor. It's kind of an assumption that you can assume, but it is applicable to any system. I would say other applications to be considered is communication networks. We have, I think, in one of the papers we have some of these examples. You can apply it to other utility networks, such as water, gas networks. Similar problems can be formulated there when you try to control some of the elements in the water network, for example. Wind farms, actually. This is a very interesting application that Sean was mentioning. Again, wind farms are even more complicated kind of creatures, right? Because the wind farm itself, they can be interconnected via a network, but the wind farm itself is a creature that is unknown, right? You kind of need to probe it and see how it works to make sure that you do something reasonable with it. So it's kind of another application. So yeah, I think the kind of wide range of applications. If you are interested in this real-time optimization, and again, there kind of there is tons of application in process optimization, for example, I think, but people already did it, I guess, even before. So.
And okay, it seems that people are really curious. So 2 more questions, and then we call it to the end so that we can let people go to sleep in Europe and whatnot. So Ronnie is asking, physical noise shocks due to solar and wind volatility and whatnot have non-trivial correlation structures. Are you trying to account for these in some way? Like, do you need to, take these into account, any specific consideration or special considerations, because these shocks could be, have unusual characteristics, I guess, fat tails, whatnot.
So I guess it's more a question of a noise that is really abrupt and have a high impact on the system rather than just small changes.
Yeah,
if I understand correctly.
Not here, probably, but yeah, like something abrupt and.
Yeah. So actually, yeah. So again, this kind of, in the analysis, it looks bad in the analysis because it will just come in the worst case sigma, right? Remember, sigma is the worst case variability of the optimal trajectory. So if you have a shock or you have abrupt change, the sigma will be very big. It means that this thing will be probably useless. But in practice, you can see that it can happen also like here, right? Here, there was a shock. So what happened here, there was an abrupt change in network topology, and the voltage dropped in a step fashion, right? And what the algorithm did, it just, okay, it had to absorb this shock, but it was able to bring the system back to stable operation. Of course, if these shocks are happening every second, then I mean, what can we do, right? So, yeah. But if there is enough time between shocks or between these abrupt changes,
somehow the time scales will matter, right?
Yeah.
And you need to know some, like you have to have some prior information, like even the definition of the optimal trajectory involves expected timescale constants.
Right.
So the final question, so could this be applied to determine optimal pricing in two-sided platforms like ride-sharing platforms? Sorry.
Can this be applied to determine optimal pricing in two-sided platforms?
Yeah, it's like you have two types of agents interacting with each other, the provider and consumer, and you're trying to set the price. Well, you can say that. Well, that probably requires some further thought.
Yeah, I think it requires some. I need to understand the problem a bit better. Let's say so. But again, these methods, again, as they put here in the slides, they kind of useful if you have a system that you want to optimize, but you don't know what the system is going on, what is going on inside the system, but you are able to measure the outputs that are of interest, right? And if they are measured, fast, exactly. So fast enough to cope with changes in the system. If you are not able to measure, if you measure them once in an hour, then who cares, right? I mean, you cannot do anything. But if you're able to measure fast and you don't know the system, then you can do something. Otherwise, and then if it fits, then it fits.
So the answer is maybe yes.
Maybe yes, but I will be interested to see the problem, because it's kind of interesting. I'm looking for more applications to these methods, and it would be great to have.
I just sent you a private message with the Discord server address, so you can open that, and then I ask people to ask further questions there, and thank you very much for the very interesting talk. And let's call this the day for today. And I hope to see you everyone tomorrow. All right. So thank you, Andrey.
Thank you again. Thank you again for inviting me. That was very, very interesting.
Interesting for us. Thank you. Thank you, Sean.
Bye.